Alright, this is the last section from Chapter 8, and this is confidence intervals for one population mean when the standard deviation is unknown. When the standard deviation is unknown. Alright, so now back in Chapter 6, we studied the standardized version of X. Well, this is the standardized version of the sample mean. Now, it looks very similar. Back in Chapter 6, we had that the standardized version of X was this. Now notice the difference between the standardized version of X and the standardized version of the sample mean. Number one, instead of X, we have the sample mean. But look down here where our standard deviation is. What does this represent? At this point in the semester, you should know what this represents. This represents the standard deviation of the sample means. Okay, that's what that represents. So really what we have here is we have this. Okay, but since you have to be able to find the standard deviation of the sample means, we write this formula in here like this. Plus, we don't want you to get this confused with this. Okay, this is the standardized version of X. Okay, standardized version of X. So please don't get this confused with what happened in chapter 6. Now, what if the population standard deviation is unknown? In other words, what if our sigma is unknown? What if our sigma is unknown? Well, we then have to base our confidence interval on a t variable. And what this is what we do is we change our standardized version of the sample mean. Instead of a z-score, this is a t distribution. Okay, this is a t distribution. Now notice the slight change here. What does S represent? Notice before we had this in there. Why is that an S now? Well, this right here is population standard deviation. Well, we just got finished stating that the population standard deviation is unknown. So S represents the sample standard deviation. So the standard deviation of our sample. So you'll be asked to find that. So and you know how to find the sample standard deviation. We did this earlier in the semester when we found things. You found the standard deviation using the computing method. Go back and look at your formula chart. Back at the very first, I believe it's chapter 3 is where you need to go look, and you'll see the formula, the computing formula for the sample standard deviation. Okay, so that's basically the only difference. It changes it from a z-score to a t-score. It changes it from a normal distribution with a z to a t distribution is what we call this. We call it a t distribution. All right, so how is a t distribution different from a normal distribution? Well, look, here's our normal distribution with z right here. Okay, notice how it's normally distributed, very symmetric looking, nice normal distribution here. Well, this is the t distribution. T distributions are not necessarily normally distributed. Okay, so that is the major difference with them. If you notice, it's approximately normally distributed. It's not going to be exact, and the reason is we have to estimate that sample mean, that sample standard deviation. So because we're estimating that sample standard deviation, we're off a little bit. So when you get large numbers of samples, if you're off a little bit several times, it starts being off a lot. And so I hope that makes sense. But here's our studentized version of the sample mean. This is what we just talked about. Now, right here, you'll see n minus 1 degrees of freedom. Degrees of freedom is our label for our t-distributions. Degrees of freedom basically is one less than the sample size. One less than the sample size. It's what we use to identify a t-distribution, because there's a different t-distribution for every sample size. The standard normal curve, there's a reason we call it a standard normal curve. It's pretty similar for all of them. Now, it can be thin, it can be more flat, but it's still a standard normal curve. The t-curve can be different for every different sample size. So in order to do that, we have to have a label for these sample sizes, which we call the degrees of freedom, which is found by the sample size minus 1. Okay, so the sample size minus 1. So if you notice, if you look down here at our graph, it shows your standard normal curve, which would be our z-curve, in green here. Well, let me go back. It shows our z-curve in green. Now, notice here's a t-curve with a degree of freedom of 1 in blue here, and here's a t-curve with a degree of freedom of 6 here. See how different they are? Depending on the degree of freedom, your t-curve is going to be different. Okay? So, here's some basic properties of t-curves. The total area under the t-curve equals 1. That kind of sounds familiar, right? Sounds like a z-curve. A t-curve extends indefinitely in both directions, approaching but never touching the horizontal axis. That sounds like a z-curve. A t-curve is symmetric about 0. That sounds like a z-curve. As the number of degrees of freedom becomes larger, the t-curves look increasingly like the standard normal curve. So the larger the degree of freedom, the more it's going to look like your standard normal curve, okay? But most of the properties sound very similar to your z-curve properties. So let's look at this. For a t-curve with 13 degrees of freedom, determine t sub 0.05, that is, find the t-value having an area of 0.05 to its right. Now, if you remember, back earlier in the semester, we had z sub alpha, and we said alpha was the area to the right. And so we had to subtract alpha from 1 so that we could get the area to the left over here when we got ready to flip to the back of the book and look at table 2. We had to use that area to the left because all the values in table 2 for the z-scores were to the left. Well, that's not the same thing here with the t. Now, this is t sub alpha. Alpha still means area to the right, but the t values, like you see in table 4, this is table 4 in Appendix A in the back of your book. I would turn back there so you could see it. This is just a snapshot of it right here in table 8.4. Alpha still means area to the right, but notice, look at our curve. If you turn back to table 2 right now, get your book, pause the video if you don't have it, get your book, turn to the very back of the book, Appendix A, table 4. If you look up at the graph in the top right, left-hand corner of that chart, it's the area to the right. Okay, so these numbers in this table are actually based on the area to the right. So no subtraction necessary to try to get area to the left like we did with the z-curves. You can actually use the alpha value to read the table. So what you're to do here is we're to find our degrees of freedom. Well, it's 13 degrees of freedom, they said in the problem. So we're going to go down table 2 to where it says 13 degrees of freedom. Okay? down table 2 to where it says 13 degrees of freedom. Now, once you find your degrees of freedom, go over to find your appropriate t value. Well, this is t sub 0.05. So find that, which is right here, and go down to where you meet your degree of freedom. So 1.771 would be my answer. That would be the t value for an area of 0.05 to the right. So this would be our t value. So this value, this t value, would equal 1.771 using our table 4 in the appendix. Now remember, it is red to the right, area to the right. It's not like our z-score tables, our normal curve tables back there in the back on table 2. If you're back there at the appendix now, if you'll flip back a couple of pages, you'll see table 2 there. And you can notice, look at the graphs of table 2, they're all to the left, shaded to the left. Remember, we read those tables from the left. Well, the t-curve tables you read from the right, area to the right. So it's a little different. People tend to get these confused, so be careful. Make sure you practice this immensely looking at these tables, okay? I'll provide the tables for you on test day, but you're going to have to be able to read them, okay? So it's all about knowing the degree of freedom and knowing that area to the right, and you'll be able to read the table fairly simply, okay? All right, so we can actually find confidence intervals using a one mean t-interval procedure. Now, we had a one mean z-interval procedure before when we knew the z-score, when it was a normally distributed set of data, but now this is a t-score, I call it a t-score, a t-curve, okay? And with this t value, we have to do our confidence intervals just a little bit differently. And I want to point out some of the differences in our confidence interval here. Notice we are finding the confidence value, we are finding alpha the exact same way. But instead of table 2, we're looking at table 4. Remember, when it was the z interval, we were looking at table 2. Instead of z alpha divided by 2, notice it's t alpha divided by 2. Here we're having to do degrees of freedom. So that's the differences in step 1, similarities and differences. In step 2, similarities, we still have the sample mean. Note, here is a difference. With the z interval, remember it was z alpha divided by 2. With the z interval, we had the population standard deviation. Here we have the sample standard deviation. So you will have to find the sample standard deviation for this in order to plug it in these formula. So those are two areas in this formula. This is the differences in this part of the formula. Notice what it says. This is found in step 1. X bar and S are computed from the sample data. So you're actually going to have to compute those. But then we interpret it much the same way. So we're doing a lot of what you're going to figure out very quickly is that we're doing a lot of the same kind of procedures, just calling it something a little different, has a little different meaning to it. It's not normally distributed, so or not necessarily normally distributed, I should say. So it's a t-value because we're dealing with the sample population standard deviation instead of we're dealing with the sample standard deviation instead of the population standard deviation. So that's really what defines our t-distribution, is the fact that we are dealing with the sample mean to get our t-value and the sample standard deviation. So we're dealing where z-scores are based primarily on the population. The z-score or the t values are going to be based primarily on the sample. So that's where the differences are between these two. So please don't get them confused. We will be, even though we will be doing much the same procedures, I will call your attention. Uh, the assumptions. Make sure they fall into the right areas. You want either a normal population or a large sample, or else you may not want to do this procedure. Okay, if it's a moderate or small sample, probably 8.2 is probably not the kind of procedure you want to use. Okay, just letting you know that ahead of time. All right, so let's look at an example. Pickpocket offenses. The FBI compiles data on robbery and property crimes and publishes the information in population at risk rates and selected crime indicators. A simple random sample of pickpocket offenses yielded the losses in dollars shown in Table 8.5. Use the data to find a 95% confidence interval for the mean loss of all pickpocket offenses. Well, first things first, I want you to um, I want you to write down this table, because I'm not going to go flip back and forth on the slides. So I want you to write down this table. So pause the video, write down the table so you have it to look at, and then we will proceed on. Okay, so at this point, what we're doing here is step one. Before you do anything, just like with the one mean z interval, do your normal probability plot. Make sure this is a normal distribution. And if you notice, we have a linear normal probability plot. It's pretty much linear, so it is a normal distribution. So that's a good thing, because here's the reason why. We only had 25 samples. 25 is a moderate number. It's not a large number. If you remember back to where we were discussing the differences in sample size, and we talked about how certain sample sizes give us more confidence than others. We said that anything less than 15 was a small size, anything between 15 and 30 was moderate, and size 30 or more was great. Size 30 or more, you can do any of these procedures pretty much. But size 15 to 30, you kind of have to look at the normal distributions. So there's 25 samples in this sample size. So in order to determine if we can use the one mean t interval, we need to do the normal probability plot so that we can tell if we can use it or not. Now, because this is pretty much normal, what we have to do, we can actually use this. We can actually use it. For small size, I wouldn't necessarily recommend it. But for moderate sizes, if you do the normal probability plot and it looks normal, then you can go ahead and use it. All right, so at this point, write down your table. So let's go ahead and start working this out. So step one, we're finding a 95% confidence interval, remember. So step one, a 95% confidence level is what we had. So in order to get alpha, we subtract 1 minus 0.95, and that gives us 0.05. So that gives us our alpha, okay? That gives us our alpha. Now we can use this alpha when we go to our t-table here in just a moment. We're going to use our alpha. Now remember, we're trying to find not t sub alpha, but t sub alpha divided by 2. If you go back and look at your procedure in the purple box that we had earlier, we're trying to find t sub alpha divided by 2. So what we're actually trying to find here is t sub 0.025. Okay, that's actually what we're trying to find. But first, we need to figure out what our degrees of freedom are. Well, we had 25 samples, so it's 25 minus 1, which is 24. So this number and this is what we're looking at. So go to Table 4, in the back of the book. And the first thing you want to do is you want to find where the degree of freedom is 24. And then you want to find your t where the alpha is 0.025, like it is over here. And scroll down and see where they meet. And they should meet at this number here, 2.064. So go to the back of your book and look at your table 4. Make sure you can identify how I got that 2.064, okay, by scrolling down the table. All right, so there's your 2.064. All right, so that's your t sub alpha divided by 2. All right, so we have that done. Now, what's some other things we're going to need? So we've got that. That's one thing we're going to need. We know our confidence level, okay? Well, we're going to need to know x bar to be able, then this is step 1, all step 1, by the way. We're going to need to know x bar. So, in other words, take that table that you wrote down, hopefully, add up all the values and divide by 25 because there are 25 values there. Add them all up, divide by 25, and you should get a sample mean of 513.32. 513.32. Well, something else. We're also going to need to know the sample standard deviation. So go back to your formulas. This will be a good opportunity for you to get some practice in. I'm not going to work this for you because we've done this so many times before. But this will be a good opportunity to get some practice in. And if you still can't get it, ask your instructor what you're doing wrong on it, because this is a chance for you to practice plugging it in the formula to see if you can get it. What we want to do, take the table that you copied down, and we want to find the standard deviation of all those values, just like we did back in chapter 3. So go to your formula table, and you're wanting to look at the computing formula. The computing formula for standard deviation. Use it for sample standard deviation. Use it and find your standard deviation. And if you do this correctly, folks, your standard deviation should come out to be 262.23. 262.23. Now, all of that is step 1. Step 2. We need to find our confidence level. Well, here's how we find our confidence level. It's x bar minus t alpha divided by 2 times the sample standard deviation over the square root of the sample size to x bar plus t alpha divided by 2 times the sample over the square root of the sample size. So you should have found all of this information in step 1. It's just a matter of plugging it in now. So we know that the sample mean is 513.32. We know T alpha divided by 2 is 2.064. We know the sample standard deviation is 262.23. We know n is 25, so the square root of 25. To the same thing, the only difference is it's going to have a plus sign here. And so at this point, this is what you should have. Then it's just a matter of you doing the correct arithmetic. So punch that out in your calculator, and you should get 405.07 to 621.57. So what does this mean? Step 3 would be interpretation. Well, we are 95% confident that the mean loss of all pickpocket offenses falls within these are dollars, so falls within these $2 values. So we're 95% confident the mean falls between $405.07 and $621.57. That falls somewhere in there. 95% confident. So you see, this is much like what we did with the Z interval procedure. It's just doing it a little differently with the T-table. Okay, so hopefully that makes sense to you. Hopefully that was fairly simple. I feel like if you can figure out the T-table, which I think is easier than the Z-table actually, because the alpha means to the right. You're not having to do all that subtraction in the beginning. But I just think that'll be easy for you. And if you can do your mean correctly, your sample mean correctly, and your sample standard deviation correctly, this is just knowing the formulas and plugging it in. And if you can plug it in, it's going to be much easier for you. Okay? This should be something that you could get very quickly. Alright, so now look at this. The whole reason I point this up here, this was a problem. We're not going to work it out or anything. But the whole reason I put this in here is because I want to show you what happens when you actually have an outlier. Alright, so the U.S. Department of Agriculture publishes data on chicken consumption. So they've taken a table of 17 randomly selected people, and they're trying to find the confidence interval. Now, we're not going to find the confidence interval, but they're trying to find it. Okay? So, the first thing they did was the normal probability plot. Okay? And this is of the 17 samples. This is the plot that came up for the 17 samples of the original data. Now notice, look at this outlier down here. That is zero consumption. So, what explains that outlier? Well, it could be data error, collection error. It could be someone who was a vegan who didn't eat chicken. Okay? Something strange that just didn't fall in what you were trying to observe. Okay? Now, just because you have an outlier, we've said if you can remove it and look at the line and it's still normal, then you're good to go. You can continue to use your interval procedure. Right now, we can't use the interval procedure because of that outlier. The question is, can we remove it? Well, if you look at it after it's removed, this is what it looks like, and that's a normal plot, and we would be able to use the procedure. We could use the procedure if we remove it. Now, here's the problem. Use procedure 8.2, the T-interval procedure. If we do not have a standard deviation that's known, because remember that's the whole point of doing the T-distribution, is the standard deviation is unknown. Okay, the standard deviation is unknown. That's the whole purpose for doing that. Now, the Z-interval procedure is when the standard deviation is known. So this is when the standard deviation, population standard deviation, is unknown, and Z-interval is when the population standard deviation is known. Okay, so that's when you're going. If you're asking yourself, how do I know when to use T-interval and Z-interval? It just depends on if the population standard deviation is known or not. If it's known, Z-interval. Unknown, T-interval. Okay, and you're going to use the samples that way, because remember, the T-interval is based on all the samples. You use the sample standard deviation, sample mean, so on. Okay, now back to our problem. I'm sorry, I got off on my soapbox there. Okay, so if we're looking at this, we could use it here because this is normal. This is a normal distribution now. But here's the problem. You've got to have a justifiable reason to remove an outlier. You can't just say, oh, there's an outlier, pluck, and remove it. Because what if it's not error? What if it truly is an outlier? So you've got to have a justifiable reason. And we do here. Okay? Because notice, this is where no chicken is consumed. So the way you could remove this justifiably would be to make your sample of only people who eat chicken. Do your sampling of only people who eat chicken. Then you could remove it. Then you could use your procedure like we did in this other graph, okay? And so you would be able to figure it out. So let me repeat this again. Simply removing an outlier because it is an outlier is unacceptable statistical practice. You need to take careful consideration and have justifiable reasoning as to why you removed it. That's the whole point of me showing you this. Now, if you were to work this out, if you had the table data and everything, which you do in your book on page 329 if you want to go for it, and it will give you some good practice at working out the T interval procedure. If you want to do that, be my guest. It can you should get a interval of 62.3 to 72, which means we're 90% confident that it falls within this interval if you go back and try to work out that confidence interval, which in my opinion wouldn't be a bad idea for you to do just to get some practice. But it is in your book. The data, I should say, is in your book so that you can practice it if you want to. That would be the answer that you would get if you did it correctly. So go back and practice it. See what you get. Okay, see what you get. Make sure you remove the outlier, and then see what you can. Make sure you remove the outlier, and then see what you get. See what you get from your. I'm sorry about that. Make sure you remove the outlier, and then see what you get from the data that's left. Okay, that would be something that you can do to get some extra practice that would help you on your confidence intervals. Otherwise, just use this example to give you an idea of what to do with outliers. All right, so that's the end of chapter 8. Z intervals and T intervals, all about confidence intervals. But remember, Z interval is used when the population standard deviation is known. T interval is used when the population standard deviation is unknown, and you have to use all the samples, the sample standard deviation, the sample mean, with the T intervals. All right, so have a great day.